Okay, for the preparations of carbonyl compounds, we're going to prepare them in sections. Now, the ways to prepare carbonyl compounds are reduction, oxidation, ozonolysis, Friedel-Crafts acylation, Rosenmund's reduction, and we can get them from carboxylic acids. These are one of the few ways to get. I think there are other one or two extra ways as well, but in subsequent videos we'll add them. Now, for these preparations of carbonyl, these are the common ways to get carbonyl compounds. So we're going to look them. I'm going to do them in sections. So I'll prepare alkanals, and I want to look at how to prepare alkanones. So alkanals, how do you get them? How do you get them from oxidation? Now, quickly, for alkanals, when you oxidize alkanal with when you oxidize when you oxidize primary alkanols, so when you oxidize primary alkanols partially, not on complete oxidation, please, partial oxidation of primary alkanols, you're going to get alkanals. Partial oxidation, that means not complete. Now, because normally if we oxidize primary alkanals, we have to get primary alkanols, pardon me. If we oxidize primary alkanols, we're going to get alkanals as intermediate, and finally alkanoic acid. So if reactions are not controlled, primary alkanols are oxidized immediately to alkanoic acid. Say ethanol, for instance, oxidation of ethanol in the presence of chromic acid or K2CrO2O7 in H2SO4, you are going to get methanoic acid if you oxidize methanol. But on controlled condition, how do you control the condition? You control the condition by making the alkanols more in excess. So excess alkanols with a very small amount of oxidizing agent, you might not be able to proceed fully or totally to alkanoic acid, as a majority of the compounds of the alkanols will be converted to alkanes. Yes, so oxidation is one way to get one way to prepare alkanals. Oxidation. So oxidation of primary alkanols, mild oxidation, not complete oxidation, mild oxidation. So we're going to use oxidizing agents. Very important. The oxidizing agents we use are the most important. Oxidizing agents such as KMNO4 in acid. Yes, acidified KMNO4, it's stronger than alkaline KMNO4. So we might also use alkaline KMNO4 because we need this thing to be partial. Or we use chromic acid. Now, or we use K2CrO2O7. So these are popular oxidizing agents I can use. So let me just list them. I can use KMNO4, alkaline or acidic, but for this kind of reaction, I'll prefer alkaline because I don't need the alkanols to become alkanoic acid. I want them to become alkanas. So we'll stop there. So use KMNO4, we use K2CrO2O7, yes, also alkaline condition. Then we can also use chromic acid. Chromic acid is K2CrO2O7 in H2SO4. Now, this reaction can occur and will produce a compound such as H2CrO4. This is chromic acid. Yes, in some cases we get H2CrO2O7. This is dichromic acid. So this is dichromic acid. This is chromic acid. This mixture can give you chromic acid. So any of these oxidizing agents we use are making the alkanols more. Any of these oxidizing agents we use making the alkanols more, we get alkanals mainly. Yes, there might be little trace of alkanoic acid formed because the alkanols are more. The oxidizing agent is lesser, is limited, so the reaction will stop halfway or stop at the intermediate. Most of the reactions stop at the intermediate. So ethanol, a primary alkanol gives me ethanol. Yeah, how do you know primary alkanols? Primary alkanols are the 1-ors, propan 1-or, butan 1-or, the 1-ors. The 1-ors, I call them the 1-ors, ethanol and methanol. So any 1-or you have, ethanol and methanol, is a primary alkanol and can be oxidized to alkanals. So that's how you get them on oxidation. So without wasting much time, what's the second way to prepare alkanals again? Second way to prepare alkanals is on reduction. So I'll quickly look at the second way. So these are the oxidizing agents. If you care to put them down or care to write them down, these are oxidizing agents I can oxidize. So let's use a case study. So in case you are writing, this is CH3, CH2OH ethanol. On any of these, let me label them A, B, C. On any of these oxidizing agents on the arrow, on top of the arrow. It's not a catalyst, an oxidizing agent. You're going to get CH3CHO. So this is ethanol, this is ethanol. Please don't forget, alkanals, the general formula of CnH2n plus 1 CHO. Please don't forget that. So, I would like to always tell students this. I like to tell people, I'm always tutoring this, that for here, n is greater than or equal to 0. So, n can be 0. 0. When it is 0, it is methanol. When it is 1, it is ethanol. So, please take note. This is an alkanal. So, usually this is oxidation. So, this is oxidation. This is ethanol. Ethanol. This is ethanol. So please, any of these oxidizing agents we do fine. So moving straight to reduction without wasting time. Moving straight to reduction. How do you get alkanals or reduction? Alkanals or reduction. So reduction. Number 2 way to prepare alkanal. Reduction. So reduction of what basically, and what is the reducing agent? So reduction of alkanoic acid or alkanoic acid derivative partially, come again, partially gives you alkanal, because if they reduce alkanoic acid or their derivative totally, you are going to get alkanol. So when you reduce them partially, you get alkanals. Reduction of alkanoic acid derivative partially, you get alkanals. So let me use a simple one for you. Let me try a simple one. Now let's say we use this. Now CH3C, please watch, oh, CH3CHCOOH. This is ethanoic acid. Okay, ethanoic acid. So ethanoic acid, if you apply a reducing agent such as LiAlH4, which is iupacly, or pardon me, the iupacly nomenclature is lithium tetrahydroaluminate 3. If you apply this reducing agent on this ethanoic acid, you are going to reduce the ethanoic acid to ethanol, a primary alkanol. Yes, so you're going to get CH3CH2OH. Yes, you're going to get ethanol. I don't normally talk about the mechanism in this kind of tutorials, because the mechanism, if I was to talk about the mechanism of this reaction, it would just be a video, just one video, to talk about the mechanism of the reaction. But basically, if I should just do a simple thing, what's happening? Let's say I'm assuming we are applying for a reduction is the addition of hydrogen normally. So it's like adding an hydrogen here. So I added 2 hydrogen and I remove 1 oxygen. Yeah, that's what I did. So I added 2 hydrogen here. So what I did is that I remove this guy, add 2 hydrogen. So yeah, so that's what we did. So basically, so that's how it is reduced. Now, but to get ethanol, now remember this is ethanol, a primary alkanol. So to get ethanol, we use a mild reducing agent. So how can we make reducing agent mild? How can we make reducing agent now? A mild reducing agent we can use is LiAlHBuTO3. So what's the name of this reducing agent? Now this reducing agent is called, many write it like this, OBUT. So this reducing agent is called lithium hydrido tributoxide aluminate 3. I come again, lithium hydrido tributoxide aluminate 3. This guy is a weaker reducing agent compared to this guy. A weaker reducing agent compared to this guy. So if this guy was to reduce ethanoic acid, we get a 70% chance of having ethanol and not ethanol. So this guy reduces ethanoic acid to ethanol. So I can, instead of using this guy that is stronger than this one, I can just say let's use LiAlHOBUT3. So ethanoic acid this time will be reduced to ethanol. So ethanoic acid is reduced to ethanol. Yeah, so ethanoic acid is reduced to ethanol. Yes, so this is reduction. This is reduction. This is reduction. This is another way to, what's it called? This is another way to what's it called? Another way to prepare alkanoic acid. So another way to prepare alkanoic acid. So this is another way to prepare I said alkanoic acid, another way to prepare alkanals. So reduction using mild reducing agent. So any acid derivative we take, let's say we use acid chloride. This is an acid derivative. So watch out for our videos on carboxylic acid derivative. Carboxylic acid derivative are acid chlorides. I can have esters. Yes, esters. If you have not gotten that, just check our other videos on carboxylic acid derivative. We're posting one soon. You can get esters. We can get many other carboxylic acid derivatives. We can have carboxylic acid anhydride. So they are basically compounds you can get from carboxylic acid. Any derivative, one of them is acid chloride. And how do you get carboxylic acid derivative? The derivatives are actually gotten by removing the OH. Yes, carboxylic acid derivatives are formed when the OH is replaced by another group. So when the OH is replaced by chlorine, for instance, you get acid chloride. So basically, now let's take this acid chloride now, this ethanoic acid chloride or ethanoic chloride, or many call it acetyl chloride trivially. So acetyl chloride, when reduced using this reducing agent, when reducing this reducing agent, you are going to get ethanol plus HCl. Yes, you get ethanol plus HCl. So reduction of alkanoic acid or alkanoic acid derivative from mild reducing agents like LiAlO-BuT3, we call it lithium hydroxide aluminate 3. Reduction of alkanoic acid or alkanoic acid derivative with this reducing agent to stop you at the alkanals. So ethanol, we give ethanol. Ethanoic acid chloride, when reduced with that same reagent, gives you ethanol also. Now, there's a special reduction I would like to talk about, a very special reduction I would like to talk about for alkanoic acid derivative. So quickly, now that reduction is the use of a catalyst we call the Rosenmund catalyst. Now, Rosenmund did a reaction. Now, the reaction is this: Rosenmund's reduction. Please, if you have not taken this down, please take it. We are wiping it off, or pause the video and get it. So I'm taking it down. So Rosenmund, Rosenmund, Rosenmund did a reduction, and the reduction is called Rosenmund's reduction. So it's still under reduction. Rosenmund's reduction. Rosenmund's reduction. Now, what's the reduction about? Reduction talks about the reduction of acid chlorides, basically or mainly, though many other alkanoic acid derivatives can undergo this reaction. Alkanoic acid chloride, like this guy acetyl chloride or ethanoic acid chloride as you call it, because I said this is ethanoic acid if you are following me. When you replace the OH with chlorine, you call ethanoic acid chloride. So the chloride, when you add hydrogen to it, it is more like hydrogenation. If you are not aware, hydrogenation is a reduction reaction. Yes, when you're adding hydrogen to a substance, you are reducing the substance. So please take note, reduction is the addition of hydrogen. So when hydrogen is added to acid chloride in the presence of palladium in sulfur or palladium poisoned with sulfur catalyst, this reduction is Rosenmund's reduction. And normally what happens is that the acid chloride the acid chloride is reduced. The acid chloride is reduced to alkanals instead of going to alkanols. Normally, if we reduce acid chloride or we add hydrogen to acid, we are supposed to get alkanols. So, but in the presence of palladium, not just palladium, now poisoned with sulfur. So the sulfur poison is reducing the effect of the catalyst, if we say so. So instead of reducing the acid to alkanols, we stop at the intermediate, which is the alkanals. So now acid chlorides are reduced in the presence of palladium with sulfur catalyst, and we get the alkanals. So you just count your carbon. How many carbon is it? 2. So the alkanal we get is also of 2 carbon. Is also of 2 carbon. So this type of reduction is known as the Rosenmund's reduction, and the byproduct is usually HCl. So this is the Rosenmund's reduction. Another way to prepare alkanals. So quickly, let's quickly look at another way to get alkanals again, another special way to get alkanals again is a third way. Before we move on, you can pause the video and get this reaction if needed. If needed, you can try others. You can put 3 carbon acid chloride, propanoic acid chloride on palladium catalyst, Rosenmund catalyst, which is palladium in sulfur. So if you hydrogenate propanoic acid chloride on palladium in sulfur catalyst, you're going to get propanal. So ethanoic acid chloride is this 2 carbon. So when you hydrogenate in palladium in sulfur, you get ethanol. So you can take that, you can try more longer chain carbons, but just know hydrogenation in the presence of palladium is sulfur catalyst or palladium is sulfur poison catalyst. So palladium catalyst and sulfur poison. So this is a catalyst poison. This type of hydrogenation is known as the Rosenmund reduction. Please take note of that. So taking it off, a third way to prepare alkanal, is from ozonolysis. So ozonolysis, yes, ozonolysis, unreductive workup. So I think we'll post I'll be dropping a video soon. That will be on ozonolysis via various workup. So now with that video, we're looking at mechanisms of ozonolysis. So now we're looking at ozonolysis unreductive workup. Yes, unreductive workup. And how is ozonolysis unreductive workup? How does it act? Now, unreductive workup, ozonolysis, let's for instance, let's use an alkene, because the ozonolysis that will lead to the alkanal production is ozonolysis of alkenes. Yes, ozonolysis of alkenes. Though alkanones can also be produced, but for alkanals to be produced, there's this particular alkenes we look at for. So ozonolysis of alkenes can give me alkanal. Now, how does it work? Now, let's say we have an alkene. Please take note of this. Let's say we have an alkene, CH3, CH double bond, CH3. Now this alkene is called but. 1, 2, 3, 4. That's butene. So, but the double bonds are carbon 2. So 1, 2. So we'll call it but 2-ene. Let's assume we have an alkene called but 2-ene. So but 2-ene on ozonolysis or reductive workup. How do you know it's reductive workup? Now, reductive workup, we have ozone. So that's the ozonolysis. Now, on ozone, in the presence of zinc as a reducing agent and water. Yes, water helps in the cleavage of the bond, splitting of the bond. So the presence of zinc and water. So this butene reacts with ozone. Now, first of all, please take note, everyone. For you to prepare an alkanal from an alkene on ozonolysis, the alkene on the carbon carrying the double bond, it should have just H. So if the carbon carrying a double bond, have more than H, does not have H, let's say instead of having H, there we have a CH3. Yes, so if the carbon carrying a double bond has a CH3, so this both of them have CH3 like this. This kind of alkene on ozonolysis will not result in an alkanal. Instead, you get an alkanol. So what I'm saying is this: when preparing alkanal, from ozonolysis of alkene, the alkene on the carbon carrying the double bond should have just H. So ozonolysis is a fragmentation reaction. It involves the cleavage of bond, especially in the presence of water. So normally what I tell people to get their product is this. Now you just quickly you break the double bond, you break it, double bond like this. You cleave the bond like this because the bond is going to cleave. I'll show you the mechanism in subsequent lesson. The bond is going to cleave. You cleave the double bond. When you cleave the double bond, you write your product. So you're going to get CH3, C. So let's say H double bond. So I'm going to wipe this off. Let's take this off. So okay. So we cleave it. So you've cleaved this bond. So you should have on this side CH3, C. Yes, CH3C, as I like to write it. Then it has H. Then leave the double bond also. So on cleaving the double bond, just add O to each side of the double bond, and that's our product plus zinc oxide. That's on reductive workup. So this product we get is ethanal and ethanol. So ozonolysis of alkene, any alkene or reductive workup, how do you know is reductive workup? Most questions in for students in the first year university level, or for students in 100 level as we call them in Africa, or for students in year one. Yeah, once they normally don't ask the mechanism, they normally just ask them question on the product. They just say ozonolysis of but2 in we give. So once they ask an ozonolysis of an alkene like that, most cases they are looking for the reductive workup, but there's an oxidative workup to it. So there's a video for mechanism of ozonolysis. But basically, how we work on ozonolysis is this. What we do is we clip the double bond, just break it. Yes, to get product for those of us in first year university level. So just break it into two. Just clip the bond. So when you clip the bond, you write the product of the cleavage to one side and the product of the cleavage on that side, leaving the double bond on them. Then add O. That's your product. So for this case, if you have been following our video, this is an alkanal. This alkanal is 1,2 carbon. So this is ethanol. This is ethanol. So ozonolysis of but2 in gives me ethanol. Now let me try out that. Let's try out that ones. Let's try out that ones. So if you're writing this, this is the product to this reaction. So this is the question. Let's say assume we have 2 question marks here. So this is the product ethanol. So let me try others. So if you're writing it down, you can quickly take it down. Let me try others. So let's say let's say now ozonolysis of prop1 in. Yes, ozonolysis of prop1 in, or the question comes like this on reductive workup. Ozonolysis of prop1 in gives, so this is prop1 in structurally speaking. So this is the structure of prop1 in. So we have CH, C, yes, this is prop1 in. Yeah, that's prop1 in. So on ozonolysis, so O3 in the presence of zinc and water for cleavage. I'll show you the mechanism. Usually ozonolysis intermediate product form is an ozonide and later a molozonide, which can later be fragmented into the various alkanals. So basically, these are the things I told you to check out for when preparing alkanals. On the alkene, on the alkene, we are using to prepare the alkanal. Now, let's check. Does the carbon carry the double bond? Does it have an alkyl group? No, there's no alkyl group. So the carbon carrying double bond just have H's. Yes, that's H. There are no extra alkyl groups. So there's just H on it. So this is 1, 2, 3. This is prop1 in. So when you cleave, this is the mechanism for any ozonolysis reaction. So you cleave. So let's cleave. So break the bond. So we should have CH3, C. We can write this H here. Then you retain your double bond on it. Plus. So clip this side. We have C. It has H and H. Retain your double bond on it. How do you finish your product? What you do, you add O to this side. You add O to this side. Yes. So adding O to both sides gives me here to be ethanol, and here one carbon alkanal. This is the functional group here. Please take note, that's the functional group. That's methanol. So this compound is methanol. So ozonolysis of prop1 in. Please take note on prop1 in. Prop1 in, ozonolysis of prop1 in gives ethanol and methanol. It gives us ethanol and methanol on the mechanism. So try out others, then reach out to me on the comment section which ozonolysis gives you problem. So any of the ozonolysis workup that give you problem, or you're asking for the ozonolysis of any alkene you're trying to fragment or split via ozonolysis, or any alkene or ozonolysis, you cannot write the mechanism, or you can't write the product, you can't get the product. So just say it on the comment section. We're going to work it in one of our videos. So for now, it will be a goodbye. In the next video, we'll look at the preparations of alkanal, and later we're going to look at the preparation and the chemical properties, physical properties, pardon me, physical properties and the chemical properties of alkanals and alkanone. So I'm going to do the chemical properties together. So they have almost similar chemical properties except for one or two few exceptions. So with that, for now, it is a bye, and we'll see you in subsequent lessons. So please don't forget to like, share, and subscribe this video if it was useful to you. Make sure you like this video. Make sure you like, it is useful to you. So for now, it's a goodbye.